This is exciting because we've come so far, and now we have so many options available to us on where we can go. So for now, we've mostly been focusing on computer vision, but there's many other fields of artificial intelligence, such as natural language processing, reinforcement learning, and anomaly detection. Just to name a few, there's so many more out there. So for this lecture, we're going to focus on one of them, which is natural language processing.
Let's say we're going to make a tool to help with writer's block. Given a few words, we want our model to fill in the rest of the sentence. The first thing we need to figure out is how are we going to represent our words as numbers? When people were first approaching this problem, one solution they came up with was to make their own dictionary. We'll take every unique word and assign it a number. We'll call this list of words our dictionary. We could then run our sentence through our dictionary to get a number assigned to each word. A function that does this is called a tokenizer. We'll start simple and create a model that takes one word as an input and tries to predict the next word as an output. Given our dictionary, we might predict that the word that comes after dog would be ate or barked. How would we set up our model to do this? Even though we have assigned each word a number, it's still a categorical variable. To treat it as such, we'll assign each word to an input. From the computer's perspective, it will assign the input word a 1 and all other inputs 0. This is called one-hot encoding because we're giving one value a 1, the hot, and everything else is cold, the zeros. For the outputs, it will assign a percentage chance that the output will follow the input word. That works well if we have a small dictionary size, but what if we have millions of words? That would result in us having millions of weights. One trick to handle this situation is to make something called an embedding. Let's say we have a dictionary of animals and we want to represent them with two numbers. We might take two ways we can describe these animals, like how wild or domestic they are, or how big or small they are. We'll assign an animal that's totally domestic a -1 on the domestic wild scale, and assign an animal that's totally wild a +1 on the domestic wild scale. This is called an embedding because we're taking something that's higher dimensional, all the animals as categories, and mapping them in a smaller dimensional space. We're using two descriptors here, so it's a two-dimensional embedding. If we use three descriptors like domestic wild, big small, and prey predator, that would be a three-dimensional embedding. A long time ago, a group of linguists tried to do this exercise where they assigned values to word descriptors. Today, we can use neural networks. Whenever we go from a higher dimensional space down to a lower dimensional space in our neural network, that's technically an embedding. In other words, whenever we go from more neurons to less neurons, we're creating an embedding. The number of neurons in the lower dimension is the embedding size. These days, people often use transfer learning for word embeddings. This follows the result of recent research. In the lab today, we'll be creating our own to see how it's done. Cool, so now we know how to map our words to numbers. However, if we're going to predict the next word of a sentence, we'll need a way to capture the previous words used in the sentence. Here, we're trying to predict the third word of these sentences, but the first word of these sentences has a significant impact on those predictions. In order to keep this first word in memory, we're going to create something called a recurrent neural network, or RNN. It will make more sense when we see it in action, so let's step through it with our cats example. Let's start off with our cat prediction. We'll feed a 1 into the neuron that corresponds with cat, and like before, we'll get a prediction on what the next word will be. When we do this, the neurons in our RNN layer are going to have a numerical output just like a normal neuron does. We're going to use the same concept again, and when we feed in the next word for a sentence, our network learns that cats at the beginning of a sentence has a specific meaning as opposed to during a different part of the sentence. We'll reuse our network again for the next word, say. When we combine this with the encoding we have from the word cats, we'll get a new encoding in our RNN and a new prediction for the next word in our sentence. In this lab, we'll be using an evolution of the RNN called the Long Short-Term Memory Unit, or LSTM. The difference is that the LSTM has its own set of neurons that act as its own memory. The goal is to capture attention. If the LSTM is fed long paragraphs of text, it does a better job of remembering key elements from that text. If you're curious to learn more about the math, check out the link in the notes below. Okay, time for some fun. Good luck in the lab.